We're coming back to vector work, and this is another way to define the multiplication of two vectors. The first way we did it was the dot product and the scalar product, and we used that for work. Now, as we're heading into applications of everything that we've learned, we're going to need it again because we're going to need it to describe rotational motion. And so we're going to start with, though, just the mathematics. And the setup is going to be something like this. Say I have a vector u that points in this direction along the x-axis, for example. Here's x and here's y. And another vector v that's like that. And we're going to say this is about 37 degrees and that the magnitude of u is 6 and the magnitude of v is 5, and the reason for picking that is so that this can be a 3, 4, 5 triangle. That's what shows up when you have 37 degrees, is a 3, 4, 5 triangle. So you can double check this, but the components of v are v is magnitude of 5, angle of 37 degrees, or you can write it as 4, 3. That's v. And u is pretty easy. U is 6, 0. Okay, just to pick easy values. So it turns out that the cross product, or this vector product, is written if we take u cross v. So I know it looks like a times, but I'm going to call it cross each time. The magnitude of this is u times v times the sine of the angle between them. The dot product, if you remember, was the magnitude of each vector times the cosine. So the dot product, if we had a dot b, that was magnitude of a, magnitude of b, cosine of the angle between them. Here, this is sine of the angle between them, and instead of alpha, I'll go ahead and write that as a phi. So in this case, just to calculate the value, phi is 37 degrees. That's the angle between both of them. And this then just becomes 6 times 5 times the sine of 37 degrees. And that equals 18, if you check that out. Okay, so that's the magnitude. But this is a vector product, so there is a direction. And the direction is really the hard part of this. The direction, finding the direction. And so the direction in this case is perpendicular, so perpendicular to the plane with the two vectors, as described by the right-hand rule. Okay, so that means it's either going to be out of the screen or into the screen because the plane is the screen where these are. And how the right-hand rule works is like this. Okay, so here's our description of the right-hand rule. Okay, you take your right hand and your first vector that you wanted to do the cross product. So we want the answer to be a cross b. So this is C is equal to A cross B, for example. And so this is the direction of vector C. So you put your first finger along the direction of A, your second along the direction of B, and your thumb points in the answer. So thumb is in the direction of the answer. And so let's try this out with our U and our V. And so what I'm going to do is switch so you can see this on in a different orientation. Okay, so here's my vector U and vector V set up as we've seen before, just drawn on a piece of paper. And so to use the right-hand rule, my first finger goes along U, my second goes in the direction of V, and so I have to kind of rotate my hand to make this happen, and my thumb points in the direction of the vector. And so in this setup, although it's a little hard for me to rotate like this, notice that my thumb is pointing out, okay? So it's out of the screen. So my hope is that you can look at the screen and take this and say, okay, my U is in this direction, my V is in this direction. Don't wrench your wrist when you do it. And then you take your right hand and you realize, okay, this is going to be, my thumb is going to be, say, out of the screen, out of screen. That's the direction. So for this cross product of, in this case, U cross V, it is equal to, well, the magnitude is 18, the direction is out of the screen. Or if we were doing this with axes, this would be X, Y, and Z would be coming out of the page, or in the plus Z direction. So that's one way to find the cross product, is to find the magnitude right here and the direction using the cross product. But we can do this component by component. And so I want to show that as well. So component by component, we can set up our components. If we take our I hat, our J hat, so our usual X and Y, and then K is out of the screen, then we can just make a little table of what happens when we cross these together using our right hand rule. So I cross J. If I put my first finger in the direction of I, my second finger in the direction of J, then for me, that comes in the positive K hat direction. I cross I. Now this is a weird one because you're going to have your fingers pointing together, but it turns out, looking back at the magnitude, the sign of the angle between them, when you do I cross I, looking at this equation again, if the angle between them is 0, sine of 0 is 0. So that gives us 0. So if I have two vectors that point in the same direction or 180 degrees apart, then the cross product is 0. And then I cross K. Again, I put my first finger in the direction of the I vector. And then my, so if I'm doing it from your point of view, this is going to, yeah, that's the same direction. And my K, like this. So I can do I cross K, and then I get a minus J hat as we go along. Sorry, putting it in the window at the same time that I'm drawing, I think the directions get flipped a little. So if I use this and I took my original U cross V and did it by components, so my U cross V in terms of components, so V is there and U is there, U would be, this would be 6 I hat plus say 0 J hat, just to be explicit, crossed with 4 I hat, a plus, not a plus, plus 3 J hat. And then I can just cross multiply these. If you like, FOIL them out if they only have 3, but they could have something in the Z direction as well, in the K hat direction. And so what I can do is I can say this cross this. If I multiply those two, that's 24 I cross I. Well, I cross I is 0 because those are in the same direction. I just look over here in my table, and then I'll do, first I'll go ahead and do it in FOIL order, outer, so that will be 6 times 3, which is 18 I cross J. You've got to keep the order the same, as it turns out. Then we'll do inner. Well, that's a 0 because it's 0 times stuff, so it doesn't even matter. And then last, that's still a 0. Okay, so the only term I have to worry about is this one. I cross J, I look at my table, that's a K. This gives me 18 K hat, which is exactly what I got up here. Magnitude of 18 in the Z hat direction. I could write U cross V is equal to 18 in the z direction or k hat direction. Okay, and so these give me the same answer. So some people really prefer to use this chart instead of the right-hand rule. It's up to you. You can put a chart like this on your equation sheet. For completeness, I'll go ahead and work all of these out, but it's worth it to check that you can verify the ones that I've done. Okay, so I've already done I. So I've got J cross I, J cross J, and J cross K hat. This equals 0. J cross K is I hat. J cross I is minus K hat. This is what I want you to notice. Look at this. I cross J, because I is the first finger and J is the second finger, gives you one direction. J cross I gives you the other direction. Instead of out of the screen, you go into the screen. So your direction changes. The order matters. This is probably the first multiplication you've run into where it matters what order you do the multiplication. Okay, so this is another kind of weird thing about this multiplication. Finally, we've got K cross I, K cross J, and K cross K. The K cross K is pretty easy. That's a 0. That's nice. The K cross I, so K cross I gives us a J hat. That's opposite up here, so that's consistent. And then K cross J gives me a minus I hat. You can see some symmetry here as we look at this. So you can just use this set of expressions as your lookup table if you're multiplying two vectors with a vector multiplication and you're not confident that you can get the answer using the right-hand rule.